Last time we talked a little bit about solving trig equations, and we talked through cosine in some detail. So let's go through that bit about cosine and just recall where this step-by-step guide came from. So if you want to solve an equation involving cosine of x, let's grab a reasonably blank piece of paper. Well, let's see it. So here's a nice big graph. There's the graph y equals cosine of x. And you know what? Let's draw like y equals 2 on there. So by looking at this graph, what are the solutions to cosine of x equals 2? Where do those two graphs cross? Do they cross? So what are the solutions? There are no solutions. So that was the bullet point here. If anyone asks you to solve cosine of x equals c, and that c is bigger than 1 in absolute value, there are no solutions, you're done. If someone asks you to solve maybe that one. Cosine of x equals negative 1/2. Well, there's a line of y equals negative 1/2. Does that line seem to cross y equals cosine of x? So there are solutions. Let's find them. And let's start by getting the simplest one. What's the solution that inverse trigonometry tells you? Well, I'll give you a hint. It involves inverse cosine. So a solution to this equation is given by inverse cosine of, Inverse trigonometry tells you the simplest solution to any trig equation. This x value is x equals cosine inverse of negative 1/2. But I have thought that we can simplify that. Today will be a good day for you to have a unit circle out in front of you. So if you don't have one out, go ahead and pull one out. Take a look at that unit circle. What's the simplest angle you see with cosine equal to negative 1/2? 120 degrees, or 2 pi over 30. I like 2 pi over 30. Today's going to be a radians day for me. So that gives me one solution to this equation. You can then get infinitely many solutions by adding 2 pi k's. There's 2 pi over 3 plus 2 pi. There will be another one at 2 pi over 3 plus 4 pi. There's this solution right here at 2 pi over 3 minus 2 pi. And the pattern keeps going both ways. So flipping back to the table, because I can't have both things projected, inverse cosine of that number plus 2 pi k gives you an infinite family of solutions. You should simplify if possible. All right, so there's like one solution. Either by looking at the unit circle or by thinking about whether cosine is even or odd or what. What's like the second simplest solution to this equation? What's the second simplest angle you see where cosine equals negative 1/2? Right here, a negative 2 pi over 3. That agree? Yeah. In general, cosine is even, so you get a second solution over here at x equals negative cosine inverse of negative 1/2 plus 2 pi k. Now, there's no plus 2 pi k there. Once you have that solution, once you have those two elementary solutions, could you now just write down all of the solutions? Oh, but you didn't say inverse cosine of negative. What did you actually say? You said 2 pi over 30, right? second one. Negative 2 pi over 3. Yeah, and that's nice. Yeah, negative 2 pi over 3 is absolutely right. Yeah. Now that we have those two solutions, we can get all of the solutions to this equation by just writing down x equals 2 pi over 3 plus 2 pi k, and x equals negative 2 pi over 3 plus 2 pi k. And that completely solves this equation involving cosine. Those ideas make sense? Let's try to do the exact same thing for sine. So, exact same thing for sine. Here is an equation. Right here I see y equals sine of x. And here I see the line y equals 1 over 3. Does it look like those two columns cross? Excellent. So this equation, sine of x equals 1 part, has solutions. Using inverse trigonometry, what's the simplest solution? As a hint, it involves inverse sine. So what's the simplest solution to this equation? Isn't it? So the input x is inverse sine of 1 over 3. And I see people reaching for the calculators. That's reasonable enough. How many people have gotten some decimal approximations for that? But yeah.
It's about 1/3. Or, oh, just the decimal.
Yeah.
0.32.
Cool. It's about 0.32-ish. It's definitely not exactly 1 over 3. It is something near actual. Awesome. So there's one solution. Inverse sine of 1 over 3, and that is this point. Take a look at your unit circle. Do you already know an angle whose sine is 1 over 3 by looking at your unit circle? Do you see an angle that gives you a y value over the No. That's fine. That means you can't simplify it. The answer is just going to involve inverse sine. But that tells you a lot already. That tells you that one infinite family of solutions is given by inverse sine of 1 over 3 plus 2 pi k. To get the other solution, this is wrong and a typo. I'm going to cross that out and I will replace that in a moment. Let's try to remember what identity we even need to use. So the solution that we just found, let's draw it on the unit circle. There's y equals 1 over 3. There's the angle that we found. Is there another place on the unit circle where where you see a y value of 1 over 3? Yeah, it's like the one on this side, right? That thing is the second solution. How would you go from that blue line to the pink line? Reflect over y-axis. What does that do to angles? What happens to angles when you reflect over the y-axis? Right, reflecting over the x-axis is kind of easy. It's just instead of rotating up, you rotate. So reflecting over the x-axis replaces an angle by negative an angle. What about reflection over the y-axis? Well, I think instead of rotating up by this much, it's like we want to start over at pi and rotate backwards. So instead of starting at 0, let's start at pi. Instead of rotating up, we rotate back. That gives us the exact same y value. So this corresponds to replacing an angle by pi minus that angle. Now that that's written, does that sound familiar? Reflection over the y-axis corresponds to pi minus theta. And as a consequence, the sine of pi minus theta is the same as the sine of theta. So I can get a second solution by pi minus the first solution. And if you like, back on the graph, that corresponds to like this point. Pi minus the inverse sine of 1 over 3. All right, cool. So now that we found the second solution, pi minus the inverse sine of 1 over 3, I can get the remaining infinite family of solutions by taking x equals pi minus the inverse sine of 1 over 3. All right, so let's extract all those ideas. I'm going to put them into a box which will give you a set of instructions to solve any equation that looks like sine equals something. So let's extract all those ideas, put them in the set of instructions. So I guess first let's deal with the weird case of that the number is bigger than 1. And I don't know, we can draw a picture of it. Does the graph of sine ever cross the line y equals 2? So what's the solution to sine of x equals 2? No. If c is anything bigger than 1, then what's the solution to sine of x equals c? There are no solutions. Sine is at most 1. We'll deal with those two specially. Let's go to the standard case. If I just give you a number between -1 and 1 and ask you to solve sine of x equals c, because remember that's all that this table is about. Step 1, get the simplest solution. The simplest solution is the one that comes from inverse sine. The simplest solution is just x equals the inverse sine of whatever the number is. And right, that makes sense. You want to solve sine of x equals c, x equals inverse sine of c is exactly what you want. To get the second solution, by what we just did above, it should be like pi minus the first. So the second solution is pi minus sine inverse of c. And let's make a quick interjection. When you can simplify, you should. For instance, I assert that inverse sine of 1/2 is a number that you know. Look at your unit circle. What's the inverse sine of 1/2? What's the simplest angle where sine is equal to 1/2? Pi over 6. So if you see inverse sine of 1/2, you can replace that with pi over 6 to get a simpler solution. And finally, if you have this solution, you have that solution, sine is 2 pi periodic, then all the solutions are inverse sine of c plus 2 pi k, and pi minus inverse sine of c plus 2 pi k. How does that set of instructions seem? Sensible? So let's close by dealing with like the oddball numbers. C equals 1 and c equals -1. And to solve those, let's literally draw a picture. So there's the unit circle. Let's suppose I want to determine when is sine equal to 1. So look at your unit circle. What's the simplest angle you see where sine is equal to 1? Right here, pi over 2. Right here a second. All right. That corresponds to like this angle. So it looks like pi over 2 is relevant. In fact, is that the only point on the unit circle that gives you a y value of 1? Yeah, it is. So that somehow means that like you should not see two infinite families of solutions, but just one. So all of the solutions will all correspond to that point. All the solutions will be given by pi over 2 plus 2 pi k. Let's play the same game for negative 1. What's the simplest angle you see where sine is equal to negative 1? Negative pi over 2. How many people would rather use 3 pi over 2? All right, there'd be no problem if you did. I'll even put both of them down as sensible things to write. Negative pi over 2 plus 2 pi k. And in fact, this is some general thing that you might find. If both you and your friend solve the same trig equation, you might get different looking answers, both of which are correct. If your answer is the same as your friend's answer, but shifted by 2 pi k, shifted by 2 pi, then adding 2 pi k will account for that. Those two infinite families of solutions give exactly the same advice, just shifted over by 1. Neato. So we have that table down. I'm going to get one more table because there's one more trig function we're thinking about, and that's tangent. And then we'll start solving equations. So let's talk through a tangent. So, and in fact, this will be relieving. Tangent of x is easier. There are no weirdo cases. All cases will be treated the same way. So, tangent equals c. There's a line at y equals c. Does it look like tangent crosses that line no matter what c is? So this equation will always have solutions. Tangent of x equals number will always have solutions. No solutions is never an option. Let's follow the same instructions to get the solution. So step 1, find the simplest solution. So that'll be the one in the range of inverse tangent. Tangent of x equals c. What's the simplest solution to that? Awesome. So this solution will be the solution at x equals tangent inverse of c. The simplest solution is x equals tangent inverse of c. Whatever that c is, and you should simplify if you can. If it's a number that you recognize, then it's a number you should fill in. And let's do that in an example. Let's compute the inverse tangent of negative root 3. Looking at your unit circle, what is the angle in the range of inverse tangent, which has tangent equal to root 2? Yeah, I meant to say negative root 3. 2 pi over 3 is spiritually correct, but technically wrong for the precise thing I asked. So let's talk about y. So this only does have tangent equal to negative root 3. I agree with that. What's the range of inverse tangent though? Yeah.
It would be pi over 2 to negative pi over 2 x squared.
So I want the one that's like between those two. So which angle is it then that I'm looking for? just negative pi over 3. And maybe I'll say this. So I said that what you said was like spiritually correct. If you use 2 pi over 3 to like start solving tangent of x equals root 3, you would get the right answer. But it's not literally inverse tangent. Nice. And once you find a solution, you can get all the solutions by adding not 2 pi k, but something else. And let's talk about what that something else should be. I guess it's also right there above it, pi k, so I'm going to write it. To find all the solutions, add pi k. Notice, not 2 pi k, just pi k. Let's talk about why. The reason has to do with the period of tangent. And what is the period of tangent? How often does tangent repeat? Yeah, it better be a period of pi for this to make sense. Let's just check that. Let's maybe label some points and convince ourselves of this. Where's that particle asymptote? One half pi. Does anyone want to remind you of why that particle asymptote is where it is? All right, let's give it a reminder. So to find the particle asymptote or tangent, so this is definitely an aside. Oh, tangent x is sine x over cosine x. So to get the particle asymptote of this, I want to know when do I divide by 0. So I guess that means I need to know when is cosine of x equals 0. And maybe by going back to your unit circle, what's the simplest angle you see where cosine is equal to 0? Pi over 2 or negative pi over 2 will do the job. So there should be a vertical asymptote at pi over 2. There should be a vertical asymptote at negative pi over 2. And in fact, there should be more of them. There should be another one over here at 3 pi over 2, and so on. All right, so let's take a look at this. It sure looks like everything between those two vertical asymptotes, if I just shift it over to be between the next two vertical asymptotes, it looks exactly the same graph. So whatever the length, whatever this length is, that length is the period of the tangent of x. And what's the length of that interval between those vertical asymptotes? What's the difference between pi over 2 and negative pi over 2? Pi. So the period is pi. So since the period is pi, if I take this point and shift it over by pi, I'll get another solution. If I shift it over by pi again, I'll get another solution. If I shift it left by pi, I'll get a solution. If I shift it left by another pi, I'll get another solution. So plus pi k. So we have now literal instructions that tell us what the solutions to trigonometric equations are. If you want to solve tangent of x equals c, the solution is inverse tangent of c plus pi k. If I want to solve cosine of x equals c, and nothing silly happens, then the solution is inverse cosine of c plus 2 pi k, and negative inverse cosine of c plus 2 pi k. If I want to solve sine of x equals c, it'll be inverse sine of c plus 2 pi k, and pi minus inverse sine of c plus 2 pi k. So I have solutions that tell me, I have these statements that just tell me the solutions to trig equations. Let's use those to solve some trig equations. Now let's start with this. Let's solve tangent of x is equal to the square root of 3. So, by following the table above, What's the solution to tangent? Well, what's the simplest solution to tangent of x equals the square root of 3? I draw pi over 3. Did anyone write down something slightly different? How many people just wrote down an inverse tangent of root 3? Cool, they're the same. So here's the first solution. Just pi over 3 or the inverse tangent of root 3, whichever one you prefer to write down. I guess root 3 is the better. Pi over 3 is the better. It's the simple. According to the instructions that we just found, once I found one solution to tangent of x equals c, how do I get all the solutions? Add pi k. All solutions, x equals pi over 3 plus pi k. Neato. All right. That feel all right? Let's solve another one. Here's another one. Sine of x is equal to negative 1 over 2. And in order to avoid you having to flip back to the previous page, I'm going to, so that you can have that in front of you and this at the same time. So I'll flip back. I'm not the boss of you. If you want to flip back and forth through the dot notes too, you can. So solve sine of x equals negative 1 over 2. So, step 1, what's the simplest solution? Yeah.
Inverse sine of negative 1 over 2.
Inverse sine of negative 1 over 2. So, the first solution is inverse sine of negative 1 over 2. And let's just check to see if that's an angle we already know. What is that angle? Do you see negative 1 over 2 as a y value on your units also? Negative pi over 6, because of the negative in front of the 1/2. So there's the first solution. The second solution, I'm going to flip back, is given by pi minus the first solution. So let's do pi minus the first solution and see what we get. So that'll be pi minus pi over 6. What is that? I hear 7 pi over 6. People agree? You disagree? Oh, okay. Okay. Let's also look at the units also. 7 pi over 6, does that give you a y value of negative 1/2? Awesome. Just a quick sanity check. It is definitely another solution. Now that we found two solutions, how do we get all of them? Add 2 pi k, because the period of sine is 2 pi, so there should be a plus 2 pi k. All solutions, x equals negative pi over 6 plus 2 pi k, or x equals 7 pi over 6 plus 2 pi k. Neato. So, I've got 20 minutes left of today. And right now, what we are capable of solving is sine of x equals a number, cosine of x equals a number, tangent of x equals a number. That should mean I can solve anything I can reduce to one of those. Let's just see an example of that. Let's try to solve this equation. 3 times the sine of x plus 2 equals 1. And I think, well, does that look like something you could reduce to just sine of x equals a number by doing some algebra to it? Yeah, I think so. And maybe just in order to illustrate the strategy I'll use to have to write down less when I do this, let's replace sine x by just the letter s to turn that into 3s plus 2 equals 1. And solve that for s. I don't think I even need to do any work. I think if I just stall for 10 seconds, he'll tell me what s is. Okay, I think that was like 15 seconds. So what's s? Negative 1 bar. Is what I just emphasized the question you were asking?
Yeah.
Okay. Yeah, sorry, legibility. So, s is equal to negative 1/3. So that means that this reduces to sine of x equals negative 1/3. Nice. This equation is now in the form sine of x is equal to a number. I have instructions that tell me how to solve that. By the table on the previous page, I'll get x equals something plus 2 pi k, or x equals something plus 2 pi k. And let's just write down the things that go in those blanks. What's the false solution to this equation?
Inverse sine of negative 1/3.
So there's the false solution. I've intentionally left that little bit of space ahead because I'm going to do one less, right? What's the second solution? You can flip back to the previous page if you need to. Yeah, pi minus the false solution. Pi minus sine inverse of negative 1/3 plus 2 pi k. And there's an answer. There's a solution to this equation. Does anyone see a simplification to make? There is one. It's not one that's been motivated by anything we've done today. Let's meditate on that negative sign inside of the parentheses. And here's like something that will be clear if you remember lots of subtle things that we did in the past. Inverse sine, even, odd, neither, all that. I hear an odd. Why odd? What got you to that? Yeah, more than just crosses the origin even. In fact, let's... Like, it does cross at the origin, but it also reflects over the origin. So you can look at the graph, it's odd. Let's see what we can use that to do. Sine inverse is odd. So that negative sign inside of the parentheses, what could I do with that? I think you just said something right there that was very clever. You can make it positive at a cost. It's odd, so you could like pull the negative sign out. So you could take this negative, instead of having it inside the parentheses, you could put it outside. That doesn't seem like a huge simplification, but I think it's nicer to see negatives outside rather than inside. A bigger simplification will happen in the second solution. I see this same negative sign inside of the parentheses. Let's pull it out and see what happens. So I could pull out this negative sign and put it in front of the sign. Does it cancel with anything now? Yeah, it's like a double negative, right? So the second solution is actually pi plus inverse sine of 1 over 3 plus 2 pi k. Minor simplification, but it's one more thing. Cool. Let's carry on. Well, I guess maybe before I carry on, any questions right now about that process? How many people think they would be likely to make that simplification if this were like a homework question? Not a disaster. In fact, it's not an issue at all on WebWalk. WebWalk doesn't care if you simplify. In fact, how many people when they're doing the WebWalk thing, before they even try to solve an equation, try to trick WebWalk into just telling it the same thing as it asked them? There are some questions where you could have done that. Do you remember when the distant past, there were some little questions about like, what's this complex number divided by that complex number? You could just tell it, well, it's this complex number divided by that complex number. It would be fine. There's a way to fix that, but that WebWalk probably wasn't fixed at the time. I think I fixed it now, so it's too late. Anyway, I'm losing track of this. Let's do another problem. Here's another one. 5 times the tangent of x plus 2 equals 1. So step 1, get tangent on its own. Let's solve that for tangent of x. And maybe I'll write down this much. If you want to get tangent on its own, well, let's play the same game. Let's replace tangent x by a name. I'm going to call it t because tangent starts with t and I'm not very creative. 5t plus 2 equals 1. And if I stall for 10 seconds, you'll tell me what t is. It can be less than 10 seconds. Negative 1/5 after 8 seconds. Does that agree with everyone? All right. So this becomes tangent of x equals negative 1/5. And now we'll play a similar game. We'll look at the flowchart this time just at the top of the page that tells you how to solve tangent equations. And you'll tell me what the solution to this equation is. What's the simplest solution to this equation? Inverse tangent of negative 1/5. And maybe one thing you should automatically do is you should ask yourself, is that a number you see for tangent on the unit solid? Is it? No. So you can't like write it down using techniques you have right now. You could use a calculator to get your decimal approximation, but I won't. So if there's the simplest solution, how do you get all the solutions? Add pi k plus pi k, and my 5 in that denominator is not very good. Let's fix that. That looks a little bit more like negative 1/5. All right. And again, I see a negative inside of the parentheses. Can I do anything with that negative sign? It's the same as negative inverse tangent. Inverse tangent is also odd. Let's remind ourselves of that by looking at a graph. That look odd? So you can pull that negative out. Let's do that. It's the same as negative inverse tangent of 1/5 plus pi k. Maybe before we move on, so inverse sine is odd, inverse tangent is odd. What about inverse cosine? Is that odd? I don't think so. I believe that. Maybe I'll ask the sequence of questions. Inverse cosine, is it odd? Inverse cosine, is it even? Inverse cosine, is it neither? Inverse cosine, is it both? Well, let's look. Let's pull up a graph. There's the graph of inverse cosine of x. If I reflect that over the y-axis, do I get the same graph again? So it's not even. If I reflect it over the origin, do I get the same graph again? So it's not odd. So not odd. So this trick that I just did with sine and tangent, it's local to sine and tangent. It doesn't work for cosine. I guess you could say, well, no, I won't. There's something you could do with inverse cosine, thinking about when cosines are negative, but I think I won't worry about that right now. So you can successfully solve equations that look like they're linear in sine or linear in tangent. And in fact, let's just increase the complexity by 1. 2 sine squared of x minus 5 sine x plus 2 equals 0. Does that look like an equation that you can solve? Does it look like the same sort of plan of attack could work? I'm not asking you what are the solutions. I'm just asking if you feel confident you could. Let's make the following first step. The thing that makes it complicated is that it's like a quadratic, and instead of x's, there are signs. So let's just replace all these signs with a variable name and see what happens. So let's replace sine by s. That'll give me 2s squared minus 5s plus 2 equals 0. That look easy to solve for s? Or easy enough anyway. Not like 10 seconds fast, but probably less than a minute. But maybe I'll suggest once you have that solved for s, conform with those around you. See if we feel confident, and then we'll come together. What if you forget for the solutions to that quadratic equation? I go at 2 or 1/2. Does that agree? Nice. All right. And right, like, even if you didn't get it in that time, like, you know what to do, right? It's the quadratic formula. I guess you could complete the square, but that seems harder in this case. So this reduces to s equals 2, or s equals 1/2. So this equation reduces to sine of x equals 2, or sine of x equals 1/2. I now have 2 solutions that I need to solve. Sine of x equals 2 and sine of x equals 1/2. Let's solve each of those one at a time. What's the solution to sine of x equals 2? Sine of x is never so big as 2. There are no solutions. How many people would have written down inverse sine of 2? Yeah, inverse sine of 2 doesn't exist, though. And maybe this is something that I don't often do in class just because of time constraints. But after you solve one of these, you should definitely check if they're actually solutions by like getting decimal approximations for them and seeing if they agree with what happens on a graph or something. Okay, so sine of x equals 2, no solutions. Sine of x equals 1/2. Oh, I wanted to switch colors. Let's switch colors. Sine of x equals 1/2. Let's follow the algorithm. What is the simplest solution to sine of x equals 1/2? Pi over 6. or inverse sine of 1/2, but inverse sine of 1/2 is pi over 6. So maybe I'll put in parentheses equals sine inverse of 1/2. So there's like the first solution. What's the second solution? What's the second simplest angle with that sign? What you answered isn't like what I was prompting for, but it's relevant. I know that that's one of the two solutions, so there's an infinite family. What's the other simple solution? Either by looking at your unit circle or by remembering what to subtract. So the second solution is x equals pi minus pi over 6, also known as cool. Is pi over 6 what you said?
No, I forgot that it was.
Oh, okay. Okay, so you had 7 pi over 6. That's an easy mistake to make. So now that we have the second solution, add 2 pi k to get all of them. So I have a minute left. So here's how I'm going to, here's my plan for the remaining of the rest of the week. Next time is a review for the midterm. We will review for the midterm. Thursday is a midterm. We will take a midterm. On Friday, we'll get back to content. And the first thing that we'll do on Friday is we'll talk through some of these same problems. In fact, that might even be ideal to make sure people remember how to solve trig equations. That won't take the whole lecture. Once we have that, we'll move on to something else. So, here's what I want you to do in the next 47 hours. There's a review for the midterm for points back on the Canvas page. Do that. It's good for points back, and it'll tell you what things you need to review. There's a review on the webpage that I also handed out a paper copy of. Do that too. I just posted to the webpage the solutions. So that will also tell you if there are any things you need to review. Also, just as last time, there's a bounty on finding errors in my solution. If you are the first person to catch an error and tell me about it, you'll get a very small bonus off of it. And that bonus will allow you to get over 90%. So, in fact, work ahead. I'll allow that to get you over 100%. Thank you. And you said you do have a packet. It's just not on you?
Yeah.
Okay. Cool. Yeah. And if